Hi, this is Mr. Mitchell with another video on light. This particular video on light is going to be more about these non-visible rays than it is the visible rays of light or visible waves of light. We've already talked about how in the electromagnetic scale, the electromagnetic waves, you only see a small portion, the visible spectrum, you might say. But there are a lot of different kinds of rays or waves that you cannot see. And that's what we want to talk about a little bit in this particular video. One source of electronic waves we don't see happens to be in sunlight. 9% of sunlight has ultraviolet rays, and you can see ultraviolet rays are here. Now, the higher the number here, the lower the wavelength. Now what that means is that you have a higher frequency on the sine curve. If you have a smaller wavelength, you may remember the wavelength is measuring from crest to crest. So the smaller the wavelength, the more frequency that you have of these sine curves. So these that are up on this scale have a lot of high energy. The smaller the wavelength, the higher the frequency, the higher the energy the rays. And that's why ultraviolet rays are able to burn your skin more than just visible rays. 9% of sunlight is ultraviolet rays, and these are high energy and can cause sunburn even on overcast days. Let's go to another slide. Past UV rays are X-rays. X-rays have an even higher frequency or lower wavelength, however you want to put it, and they are more have more energy. Now here's what happens when you have an X-rays. X-rays pass through the body, but some are absorbed by the bones, and you can see a little bit is absorbed by the body. You can kind of see these faint outlines here. But since it primarily goes through the body but is absorbed by bones, that shows the bones on a photographic plate. And of course that's incredibly handy for doctors. Now X-rays, ironically, may kill living cells and turn them into cancer. And you know, if you've had X-rays, there are precautions that the doctor takes to where you don't get too much exposure. And it's kind of ironic that gamma rays, hey, we'll go back to gamma rays here. Yeah, gamma rays, which is just the next one on the scale, are actually used to treat cancer. Well, just a little nugget of information I thought I'd give you there. Now let's go to the other end of the spectrum. We talked about ultraviolet, we talked about X-rays, and just touched a little on gamma rays. Now let's talk about the ones that have less energy. Less energy, that means they have less frequency, but the wavelength will happen to be longer. Is what this wavelength will end up being. So the first is going to be infrared light on the red end of the spectrum, or just off it, I guess you might say. Now you may see here that we have a picture right here. You probably have seen pictures like this and known that the darker colors, well, I guess you'd say the red, will represent heat. And that is actually true on an infrared camera. Infrared light can measure heat. There are sensors that can track. There's also other things that can happen with infrared light, but that's kind of one of the most common things right here is infrared light can track heat, can measure heat. And it also is helpful in weather. It can track the movement of clouds and the change in heat, and can record that. So weathermen can use infrared light to help track where the heat is that has to do with the movement of the clouds. Now you may remember that the next one on the list was microwave. Microwave, hey, we've heard about microwaves. Fast cooking, even I can use a microwave. Microwaves are not near the same sine curve as a lot of others. They have a lot of distance from crest to crest relatively. In fact, it's actually in the centimeter range. Now, when we're talking light waves, we're talking about nanometers, which is something you can't even see, but centimeters you can see. Well, the most familiar use of microwaves, of course, is in cooking. These waves can penetrate into the food 3 to 5 centimeters. But wait, all food that you cook in the microwave, some of it's thicker than 3 to 5 centimeters. Now what's going to happen is you get a lot of heating from a source besides just the microwave, and it'll explain itself a little bit down here. So the microwave has a little help in its heating. Cooking's the most familiar use. Their energy, the microwave's energy, is absorbed, and the changing electronic fields of these microwaves cause water and other molecules to vibrate. So here's where the secret is, I guess you might say. These microwaves that are traveling from the machine itself will go into the food 3 to 5 centimeters, and it causes the food particles to vibrate. And that's where you get some of the heat. Sure, there's heat already coming from the microwaves itself, but the water and the vibration causes causes some of the cooking. And you may notice sometimes if you put a hot dog in too long, poof, it'll burst open. It'll burst open because of the vibrations that are inside of it. So that's a little bit about how a microwave actually heats things up. And the heat from those vibrations spread throughout the food. Now you actually, something I had not have in my notes here, but you never notice how in a microwave sometimes some of your food is hot and sometimes some of your food is cold? And that would be because of interference. Sometimes you get interference in standing waves. Do you remember standing waves? Where you have nodes and antinodes. If a portion of the food happens to be at a node, it's not going to cook as much because you don't get as much vibration. Just kind of a little nugget of information for you right now. Let's talk about some more waves. Let's see what is remaining. Radio waves. Let's talk about these radio waves. Radio waves are even longer than microwaves. Some of them are tenths of a meter, meters like 3 feet, to millions of meters. So these radio waves can really be big. Of course, you know that radio is gone through radio waves. You have a transmitter at an antenna and a transmitter at a receiver, which could be your radio, and it picks up the waves at whatever frequency. If you turn it to a different frequency, that's what it will pick up there. But it also has other uses. TV signals are also radio waves, use pretty much the exact same function. But one we're going to talk a little bit more about is radar. Now, radar is used to track, for example, airplanes. What an airplane. That's pretty bad, isn't it? Well, let's use your great imagination and assume this is an airplane. Here at Radio Traffic Control, they have big radar screens. And what happens is the control tower antenna is going to produce these waves. That's not a whole lot better, is it, this antenna? But it's going to produce these waves that are going out. And these waves going out, that of course have a pretty good distance between the crest, is going to eventually reach a signal for the airplane. And in some cases, the signal is relayed back. The waves go to the airplane, and in some cases it is relayed back. And what that does is that gives the plane's location and it gives its elevation. So they can track it on something like this down here. Now, if it's at a short range, the original signal sent out by the control tower, this original signal sent out by the control tower, will bounce back. Now, that's exactly what I said. Well, let me repeat that. If it's at a longer range, it will just hit the plane and they will know where the plane is from there. But if it's at shorter range, then it bounces back. But either way, you have these radio waves, which is going out toward incoming aircraft or whatever happens to be flying out there. And it shows up on these radio signal things such as this. Gives the plane, there's like a computer chip that kind of helps with that here. Computer that calculates the distance using the time delay it takes for it to go here and then coming back. Police radar also uses radio waves. Here we have the police right here with his handy dandy radar gun. You have a Speedy McSpeed coming in his nice red sports car. The radar gun fires a signal of a known frequency out toward the target. And of course, this just all it does is bounces back. It then measures the frequency of the reflected waves. So the radar gets the frequency of the reflective waves, and that's how it can tell how fast this is going. A computer chip takes into account the signal time and the Doppler effect to show the speed in a matter of less than a second. So waves go out to the car, waves come back, frequency is measured.